We have a Mealy finite state machine here. It's a Mealy machine because if we look at the output's defined here, and the output explicitly depends on the input. So this is a Mealy finite state machine. We need to convert this to a more finite state machine in this exercise. In a more finite state machine, the output cannot depend on the current input. So just like in the previous video where we eliminated glitches, the trick is to treat this instead as pre-computing the correct output. So we're going to change this out to next out, which is pre-computing the next output, then put it through a flip-flop so that at the next rising edge of the clock, the pre-computed output becomes the actual output. Let's do this now. Change the output to next out, so we are now simply pre-computing the output rather than computing the actual output. Then at the next rising edge of the clock, we want our pre-computed output to become the actual output. So out takes the value of next out end, and we need a place to store the next out. What we have done is we've converted the output logic into next state logic. So this is next state logic, this is also next state logic. Because we've now augmented our state, we need to initialize fully our state. So here we've initialized the variable state to A, but out is now part of our state. Here's next state, here's state. So we have to initialize out. How do we initialize out? Well, because over here we have a Mealy machine, it gets a bit interesting. We can ask ourselves, whenever we return to state A, will the output only ever be a 0 or only ever be a 1? Or can we return to state A in two different ways? So sometimes the output will be a 0, sometimes the output will be a 1. Well, if we look over here, we see that we can end up in state A via this position here or via this position here. So over here, this says that if I'm currently in state B and my input is a 0, I move to state A. So we're in B, the input's 0. If we're in B and the input's 0, the output's going to be a 1. So in this case, when we transition to state A, the output will be a 1. What about for this case here? Well, if I'm in state C and the input's a 1, I can also move to A. If the input's a C, then it doesn't matter what if the state's C, it doesn't matter what the input is, the output's going to be a 1. So in both cases, the output is always going to be a 1. We initialize out, which is now part of our state, up here, initial out 1' b 1, based on what we were just discussing. In recognition of having successfully converted this to a Moore machine, we change its name up here, and we can have a look at what we've done. We have taken the instantaneous output, so to speak, and we've changed it into a pre-computed output that we then put through a flip-flop before actually outputting it. The output logic here has become part of our next state logic here. It's important to note that these two machines are not identical, but this, if you like, is the closest approximation to the Mealy machine here. So the closest Moore machine that comes to implementing the Mealy one is this one here. We're now going to look at the same problem, but we're going to do it via a state diagram. So as an exercise, we're going to start drawing the state diagram for this Mealy machine, and then we're going to have a look at how to take the completed state diagram for a Mealy machine and convert it into a state diagram for a Moore machine. We see we have three possible states. So I've got state A, state B, state C. The starting state is given up here, so we indicate that we start at state A, and then we have to follow the different transitions. So what happens if I'm currently in state A and my input's a 0? Well, I move to state C. If I'm in state A, the input's a 0, I go to C. If I'm in state B and the inputs are 0, I go to state A. If I'm in state C and the inputs are 0, I go to state B. Do the same for the 1 transitions. If I'm in state A and the inputs say 1, I go to state B. If I'm in state B and the inputs say 1, I go to state C. If I'm in state C and the inputs say 1, I go to state A. These are my 1 transitions. What about the output? Well, because it's a Mealy machine, the output gets associated with the transitions. So if I'm in state A and the inputs say 0, then we see that we move to state C, but what's the output? If I'm in state A and the input is a 0, then the output's going to be a 0. If I'm in state B, then the output is the opposite of the input. So if I'm in state B and the input's a 0, the output is going to be a 1. And if I'm in state C, then the output is going to be a 1 no matter what. Now we do the same with the 1 transitions. So if I'm in state C and the input is a 1, then my output will always be a 1. If I'm in state B and the input is a 1, then the output is going to be a 0. And if I'm in state A and the input's a 1, then the output is also going to be a 1. Now it's probably worth mentioning the output does not change when we transition, the output changes as soon as the input changes. So I can be in state A. If the input is initially 0, then I'll be outputting 0, but I don't transition if there's no rising clock. If the input changes to a 1, then the output changes to a 1 and I don't transition. So I can be in state A and I can be sometimes about to head down here with this output, or when the input changes I can be about to head down here with this output, but I don't actually transition until the next rising edge of the clock. From this Mealy state diagram, we're going to derive a state diagram for the Moore version of this Mealy finite state machine. To do that, the first thing we do, or at least the first thing I do, is that I'm going to create all my states, but augment the state with the possible outputs. Now, some people might be more efficient and work out that in some cases you don't have both outputs, but I'm just going to do this in this particular way to illustrate a point. So if I'm in state A, my output might be a 0, or I can be in state A and my output might be a 1. I could be in state B with an output of 0, I could be in state B with an output of 1, I could be in state C with an output of 0, or I could be in state C with an output of 1. Because it's a Moore finite state machine, I need to put the outputs everywhere, but by convention, the outputs just given by the second number in my state, like this. Let's look at what happens if the input's a 0 first. So if I'm in state A and I get a 0, I go to state C. So if I'm in state A, either here or here, and I get a 0, I go to state C, but to which C? Well, if I get a 0, then the output should also be a 0 here. And so therefore, if I'm in state A and get a 0, I'm going to go to C0 to signify that I'm going to get a 0 at the output. So we can add this. Doesn't matter which state A I'm in. If I go to state C, because my input was a 0, then I'm going to be outputting a 0 here. Similarly, if I'm in state B and the input is a 0, then I go to state A and I output a 1. So if I'm in state B and I get a 0, I go to state A and output A1. So I go to the A1 state to show that I'm outputting A1. If I'm in state C and the input's a 0, I go to state B and output A1. So in state C, I'm going to go to B1. Now we do the same if we receive a 1 at the input. If I'm in state A and I receive a 1, I go to state B and output a 1. That means I go to B1. If I'm in state B and get a 1, I go to C and output a 0. So in other words, I go to C0 from B. So from B, I go to C0. If I'm in state C and get a 1, I go to A and output a 1, so I go to A1. So I'm going to come up here like this. This might look like a bit of a mess, but so be it. The next thing to work out, are there any states that I don't need? And we see immediately that, look, here's a state that we never enter. So since we never enter it, we can get rid of it. So let's have a go at getting rid of this state here. Now that that's gone, we notice that this state here also doesn't exist. And we notice that when we worked out how to initialize our finite state machine, we saw that whenever we ended up in state A, the output was always a 1. So let's get rid of the state A0 as well. There's one more state that we never enter again, so we can get rid of B0 as well. This leaves us with only 3 states, and thus we can have quite an efficient state representation. We only need to use 2 flip-flops if we so desire. Indeed, for our state representation table, we just have to work out how to represent state A1, how to represent state B1, and how to represent state C0. One option might be simply to call that 0, 1, and 2. We might decide to use one hot encoding, in which case that will be 001, 010, and 100. I should emphasize though, the fact that we lost 3 states here is quite unusual, and it's just because of this particular example we chose. Normally, you would not lose so many states. Finally, we should double check this is indeed a valid state diagram. That means that every state needs to have exactly 2 outgoing arcs, and they have to be of the 2 different colours, because we need one outgoing arc for a 0 and another outgoing arc for a 1. So if we look at this state, yes, we've got 1 green, 1 yellow going out. Look at this state, we've got 1 green, 1 yellow going out. Look at this state, we've got 1 green, 1 yellow going out. Therefore, this is a valid state diagram.